It is easy to recognize an object in motion and an object at rest. Supersonic jets, race cars, and even my minivan can be objects in motion or at rest. What keeps an object at rest or in motion? What causes an object at rest to move? Furthermore, what causes an object in motion to stop? Well, the short answer to these questions is force, which is any influence that causes an object to change its shape or motion. For example, I must apply force to move a heavy object such as my chair or a set of dumbbells. In fact, I have to apply a force, albeit not as much, to move even a lighter object such as my pencil. If I press down on a ball of clay, the force of my hand causes the clay to change its shape. In this lesson, we will explore the relationship between force and motion as explained by Newton's laws. Newton's first law of motion states that an object at rest remains at rest, and an object in motion remains in motion with the same velocity unless acted upon by what we call an unbalanced force. Let's break this law down by defining some key terms. Velocity. Velocity is the speed of an object in a specified direction. An unbalanced force. An unbalanced force is an external force that changes the motion of an object. When an object is at rest or moving at a constant velocity, all the forces acting on it are balanced. For example, my cup of coffee is resting on my kitchen table as I make this lesson. The force of gravity pulling down is balanced by the force of my kitchen table pushing up on my cup of coffee. Now, if I'm to move my coffee, I must apply an external force to disrupt the balance. Thank goodness my muscles are strong enough to apply such a force so I can enjoy my cup of coffee. Now that's good Joe. Newton's first law of motion is also referred to as the law of inertia. Inertia is simply the resistance to change in motion. In short, objects tend to keep doing what they are already doing. There are plenty of applications to Newton's first law of motion. Consider a car moving west along a highway with a constant velocity of 65 miles per hour. What happens when the driver takes his foot off the gas pedal? Well, according to Newton's first law of motion, the car should remain at a velocity of 65 miles per hour as long as the forces are balanced. As we have witnessed, however, the car slows down and it comes to rest. This observation begs the question, what external forces act on the car to stop its motion? The answer is friction. Friction is a force acting in the opposite direction of motion when two objects come into contact with each other. Without external forces, the car would continue to move west at 65 miles per hour. Now consider a golfer hitting a ball off the tee. While the ball is on the tee, it is said to be at rest. That is, it has no motion. Once the swinging club comes into contact with the ball, the club applies an external force, disrupts the state of balance, and bam, sends the ball flying into motion. Now I like coffee, so let's see how Newton's law of motion applies to drinking coffee and driving. While the car is at rest, or even moving at a constant velocity, so is the coffee. And you know what? It stays in the cup. But what happens to the coffee if you increase velocity in a forward direction? The coffee keeps doing what it has been doing and ends up in your lap. That is, assuming there is no lid on the cup. Let's break it down. When you push on the gas pedal, the wheels spin. However, the road applies a force to the wheels and pushes the car forward. The back of the seat applies a force to your back and pushes you forward as well. But what about the coffee? The coffee maintains its velocity at 65 miles per hour. And your lap actually moves forward into the coffee. Ouch! Just the opposite happens when we hit the car's brakes. The brakes slow or even stop the spinning of the wheels. When braking from a constant velocity of 65 miles per hour, the coffee tends to maintain its velocity of 65 miles per hour, and now it's going to end up on the dash of your car. The coffee experiences inertia when we brake to a stop. The coffee resists the change in motion and keeps moving forward. Likewise, we experience inertia when braking the car. You may feel yourself tend to slide forward in your seat when braking to a stop. In reality, you're simply doing what you were already doing, and the seat is moving backwards relative to your body. You would continue to slide forward in your seat unless your seat belt is in place to apply an external force to your body. We can apply Newton's law of inertia to body functions. Have you ever experienced a dizzy feeling after coming to a stop in a descending elevator? Well, better hold on to the railing. Our body and all its contents move down along with the elevator. Once the elevator comes to a sudden stop, the floor of the elevator applies an external force to our body, causing it to come to a stop as well. However, the blood in our body doesn't experience the same force in the same way. It's kind of like the coffee. The blood tends to keep moving down even after the elevator comes to a stop. The blood descends away from our head